Alright, hello everyone. Welcome back to the F equals MA Club. This is now for 2023 to 2024. This is the first meeting of the year. We're going to be going over an introduction to the FMA competition and going over some kinematics as well, along with some other materials. But yeah, it's quite nice to have everyone back, and hopefully we'll have a great year as well. So I kind of went over that, but thank you everyone for joining this year for the first meeting of the school year. I have a camera now. Well, I had a camera, but I have scenes with cameras now, so you can see me. Now I'm much bigger, and now I'm much smaller, and now I'm non-existent. But that's kind of going to be the format for this year, and let's just jump straight into it. So, just a little bit of background. So, what exactly is the FMA competition? So, this is going to be a 75-minute, 25-question test. That means you're going to get, on average, around 3 minutes per question. Now, remember, that's going to vary a lot. A lot of the questions are going to be a lot easier, and some of the questions are going to take a lot longer. And when I say a lot longer, I mean a lot longer. Some of them are going to take maybe 6 to 7 minutes if you don't plot your time well, and if you don't use any tricks, maybe even 8 minutes or 9. So it's always nice to be wary of your time management and be conscious of how much time you're spending on each and every question. So this is hosted by the American Association of Physics Teachers and I believe the American Institute of Physics every year. It's one of the 2 tests to qualify for the United States of America Physics Olympiad. So that's going to be the national level physics Olympiad. So there's going to be one test, which is the FMA exam. That's what we're talking about. And then there's going to be the qualifying exam, which is the USFO exam. And one, if you're able to pass on through that, you're going to be placed in the United States Physics Study Camp. And if you're chosen from there, you can participate on an international level. I believe last year, our U.S. team won, I think, 4 gold medals and 1 silver. I'm not sure, but there's a lot that you can do with this, and this is a great starting point if you really want to go into physics, or if you just want to learn physics overall, if it's a passion, or if it's just something that you want to learn a little bit more, or maybe it's a class you're taking and you need a little bit of help. Speaking of taking it as a class, there's going to be a few other things. So this is only going to cover, FMA exam is only going to cover Physics 1 and Physics C mechanics. Now, Physics C mechanics, not exactly, in the fact that it's mostly going to be Physics 1, but calculus is still permitted and may help in some scenarios. That's what they explicitly state, though you don't need calculus at all. From what I've seen, there's very few problems that are going to use calculus, but it will be a helping hand sometimes. Not only with some of the problems, but just understanding some of the concepts as well. So, you will be using a scientific calculator only. This is a scientific calculator. You can see I cannot graph on here. And this is also very painful to type on. So you can't use graphing calculators. That's because there's a lot of graphing problems. And there's always the concern of having programs on here, right? I don't want automated stuff. So that's why there's no graphing calculators allowed. It does make me very sad. This is very hard to type on, and I always make mistakes. But that's kind of what we're given. This is also the image that we see on screen. Which is this TI-30X2S, I think. I don't know, but this is the one that I use. It's provided by the school. And also, one final thing. This is very small. G, which is our gravitational acceleration, is going to be 10 meters per second squared. Partially because that means it takes a lot less time to plug into this calculator. It's also because I don't want to be a tryhard and be like, oh, G is equal to 9.806 blah blah. No, we don't need that. We just need to know that it's 10 meters per second squared. That makes our calculations, our equations, and that's not the focus to like memorize these digits. Some other things as well, you won't be given a formula sheet. You won't be permitted to have a formula sheet, so a lot of memorization is needed, which is kind of ironic after I just said that you don't need to memorize G, but it's just nice to memorize as many equations as you can, and I'll be going over a lot of them as we go on through this course, this club. But yeah, that's also something to bear in mind. This, again, Physics 1, Physics C, this will be teaching a lot of little tips and tricks, not only for FMA, but just for Physics 1 in general. For the USFO exam, on the other hand, that's going to cover both Physics 1 and Physics 2, and there will be a requirement for calculus on some of the problems. So it's going to be a lot harder, or not a lot harder, but a little bit harder than the FMA exam. But for now, we're just going to be covering Physics 1. If you do pass on to the USFO exam, congratulations, we can absolutely work on that stuff together. But for now, we're preparing for the FMA exam. So let's dive into the club, actually. I forgot that I added the slide. So this club is going to prepare students for the FMA competition. It's going to give you guys the opportunity to take the test in February. Now, that date isn't confirmed. I have February 9th here. That's because that was last year's. That was last year's time. You can see that's February 9th of 2023. A date hasn't been released by AAPT as of recording this video. It might be recorded right now. It might be reported right now. I'll probably announce it in a future video. I might even add a comment. I don't know how YouTube works, but it's going to be in February. That's what we know. So this club is also going to help a lot with anyone who's just in physics and needs a little bit of help. You're in Physics C, you're in Physics 1, you're in any of the APs, you're struggling a lot. You can use this as a resource. You don't even need to take this test. It's just a nice repository of a lot of problems and questions, and there's a lot of little tips and tricks that you can even use in your own classes. So currently meeting times are set at Wednesday afternoons. I plan on sending out recorded videos by Thursday. I haven't gone to this because I've been busy and also stupid and lazy, but that's why this is a little bit late, but usually it's going to be on Thursday. If I break that promise, I'm going to let you guys know, but that's what the current schedule is. Speaking of the current schedule, this is what I have for the planned schedule. So first time, we're going to have introduction, FMA exclusive stuff, and a little bit of kinematics. This is definitely going to change. You can look at this stuff and you can be pretty concerned. It's not going to be too difficult. Last year, one of my biggest problems was I assumed that you already had some physics knowledge. I might change that this year since I have a little bit more buffer time, but I'm not sure about how I should teach this. So if you have any concerns, if I'm explaining too much, too little, just let me know. If I'm going through everything too slowly and you're losing interest too quickly, also let me know in the comments. Like and subscribe. I'm kidding. But just give me as much feedback as you need, because I need it. I need feedback. But that's the current schedule for now. This is definitely going to change. I might even I'm already thinking of probably extending dynamics to 2 weeks or something like that. But this is the current planned schedule, and we have a lot of buffer. So yeah, that's what we're going to go with, and let's get right into it with kinematics first. So here are the 4 kinematics equations that are nice to know. I'm pretty sure there's a 5th one. I forgot it. No, I didn't forget it. I'm just too lazy to write it down. I think it's the average one. Anyways, these are the 4 kinematic equations that are nice to know. So remember that our velocity is going to be this v. I'm looking towards this direction because this is the only monitor that works. So if I start turning away, that's probably why. So remember that our velocity is going to be v. This 0 is going to be v naught. That's going to be our initial velocity. A is acceleration. T is time. This x is going to be our position. And this delta x is going to be our change in position. So if I had something like x naught, that would be our initial position. There's a few other symbols. We can say xi is our initial, xf is going to be our final. There's some other stuff. I'm just going to assume that you're going to know these things. If you don't, let me know. And yeah, that's basically it. And I can go over this stuff if it's completely new to us. So some other stuff. Projectile motion. Now this is going to be a big one, right? So projectile motion. I'm throwing a projectile, right? I'm not going to throw this pen. I'm going to throw this this wad of paper. If I throw this is going to become a projectile, right? I throw this, that's a projectile, right? And when I threw it, you can see there's this little curve, right? As I throw something, oh, that's my actual pen. But you can see that there's a curve, and we can even see that curve modeled in this curve. If I can click on to... if I can click onto this, we can see that there is a curve. Why can't I... Can I? No, I can't. That sucks. But you can see there's a curve here, right? There's a curve. So this is kind of the curve that something that I throw is going to follow in, right? It's going to be like this flight curve. And this is assuming that we're in a perfect physics world. So let's kind of decipher these equations, right? So the first thing we have is this x of t and y of t. So x and y, as hopefully you know, X is going to be like our x-axis. That's going to be our horizontal position, right? Y is going to be our y-axis. That's going to be our vertical position, right? So that t is going to represent like at some point in time, right? So what is our horizontal position at like t equals 2 seconds? That's going to be this equation when t equals 2, right? So we're plotting these horizontal and vertical components as a function of time, right? So we have our initial positions, right? We have this velocity component, and we have this acceleration component, right? So let's talk about each in turn. So initial position, for this case, that's going to be right here. That's our starting position, right? And next, we're going to have this v naught t cosine theta. This is going to be our this is going to be our velocity component, right? So what's this cosine and sine theta doing here? And by the way, it's going to be really nice to like memorize like just a little bit of the unit circle. Like memorize like 45, 45, 90 triangles, 30, 60, 90 triangles. Remember those side length ratios. And it's nice to remember like the cosine and sine values, right? Like cosine 0 equals 1, cosine 1 equals 0, and just remember that kind of stuff. And sine 0, 0, sine 90 is 1, that kind of stuff, right? All right, and we're probably going to use degrees. Anyways, so this cosine is going to represent the horizontal component of our velocity, right? And we can even see it in this graph, this v of x, this blue arrow, that's going to represent our velocity component. On the other hand, we have our vertical component of velocity, right? That's going to be here, and that's why our sine theta is here, and that's going to be this v of y that you see here, right? So we can say that v naught sine theta is going to be equal to vy, and as a function of time, that's where we get our t from, if that makes any sense, and I'm circling the wrong part. Finally, we can see that there's something missing, there's something very different between this x and y function, which is this minus 1 over 2 gt squared. Now, what exactly is that? If you don't remember, that g is going to be equal to 10 meters per second squared, right? That's our gravitational acceleration. So that means this is our gravity. This is the acceleration from our gravity, right? We have our position, we have our velocity, and we have our acceleration. Now, why isn't there 1 in our x? That's because we don't have any sort of acceleration in our horizontal component, right? In a perfect physics world where air resistance and friction aren't an issue for projectiles, when I throw this and or if this moves along a line, there's going to be no horizontal acceleration. It's going to keep on moving in this direction at the same horizontal velocity as before. On the other hand, gravity exists, right? If I throw this up, it's gonna come down. That's how the apple came down and gave Isaac Newton a concussion. That is not true. Apparently it was like a metaphor. I don't care. But when I throw something up, it's gonna come down, right? That's gravity. And that's why we have this gravitational acceleration here. That's because, and we can even see this here with this v of y. This is getting smaller and this is starting to go down, right? Because there's gravity. There's an acceleration that's making this go down, right? And if you want to know calculus, position, velocity, acceleration are all related to each other, and we're going to talk a little bit about that more next time. I'm already 14 minutes in, and this is like the second slide that has material. Anyways, so this is where we get to some of the FMA exclusive stuff. I know there's like one of these equations on like the on-ramps course, but I don't know what on-ramps is doing. So these are 3 equations that are very good to know. This is a Cora image. I love this Cora image. You can search up like maximum height, time, and range Cora, and this will probably pop up in the images section, and I love this so much because these 3 equations, I'm actually covering this up. Here, let's do that for now. I'm pretty sure I covered up like 15 other things at this point, but these 3 equations are going to be very key. So we have our time of flight, our maximum height reached, and a horizontal range. In my original video, I proved this. You can go back to it and check it out, but I'm not going to prove it this time. I'm already running out of time, and I'm on a time constraint. So we have our time of flight, we have our maximum height reached, and our horizontal range, right? That's all we need to know. And we're going to be going over, I'm pretty sure 2 out of 3 of these, maybe even all 3 of them, for the example problems, which I need to get to. So, back to here. So, next, we have F equals, and you know what? You're here. Where is your laser pointer? Where is my laser pointer? Give me my laser pointer. I want my laser. Thank you. Okay, so FMA exclusive material, right? All right, so first we have dimensional analysis. Now this looks really weird, right? There's like this big table and a bunch of symbols, and now I'm very confused. Don't worry, please don't be confused. If you're confused, then I'm even more confused than you. So let's go to Krita for a moment. Haha, Krita, please tell me this is working. So what is this LT-1 thing? Now, we saw that L equals length and T equals time, right? So this is saying our length divided by time. I'm pretty sure this was our velocity, right? Our velocity is going to be equal to our length divided by time. And that makes sense, hopefully, because that's what velocity is. Velocity equals meters per second, right? Speed is equal to distance over time, and this is exactly what this is talking about. That's what dimensional analysis is. It's trying to determine this kind of thing. And we're going to go over some of the practice problems for this to make it a lot clearer about what I'm talking about. So I'm going to remove all of this and go back to the slideshow, right? All right, so back to the slideshow. Next, we have error propagation. Now we're going to go over all of these, right? So I'm not going to explain this too much in depth. If you want me to explain them in depth, let me know in the comments. But this is error propagation, right? We have addition and subtraction. We have multiplication. What is this asking for? So let's go back to Krita. Let's say I have a ruler, right? Let's say, I'm going to change this to black. Let's say I have a ruler. Oh my god. V, I think, right? No. The V? Yes, okay. Let's say I have a ruler. And this ruler, if you're in chemistry, you know what this is. If I have a ruler that is 1 meter long, this is not going to be, we know that the world isn't perfect, right? We know that nothing can be perfectly 1 meter, and nothing can be perfectly some length, distance, some kind of measurement, right? So that's what error propagation is for. So let's say we have this meter stick that has some sort of uncertainty, right? Plus or minus 0.1 meters, right? This is a meter stick. This isn't going to be a perfect meter stick. It might be 1.1 meters. This might be 0.9 meters. Who knows? That's what this uncertainty is for, right? Now, what if we were to like put this together with like some other measurement? Let's say this is like 0.2 meters plus or minus like 0.05 meters, right? And we're trying to find the area of this, right? So what is the area of this? Taking into account of these uncertainties. So, okay, we can say the area of this is 0.2 meters squared, right? But what's the uncertainty? That's what error propagation is all about. And we're going to talk about this a lot more once we get to the problems. But this is kind of a little bit of a kind of, oh, I don't have, we're going to be doing some video capture. There we go. I'm here now. Hi, I'm here. So, oh, am I here? I am here. Okay, so, that's what error propagation is all about. It's trying to determine this uncertainty, right? All right, I'm gonna hide me for now, and let's go back to the slideshow for a moment since we only have one side left. So last slide, as I just stated, just some FMA strategies. These are basic strategies. Just this is something you're gonna need to know for every single test that you're ever gonna take, except for the ones that you don't. But these are the 3 strategies that you're gonna need to know. Break down a problem. Some of the problems are going to have a lot of parts. I'm pretty sure one of them had like 5 parts that I had to deal with. And it was like I don't know. It looked easy, but it was like, there was 5 parts. And there's like some where you don't even know where to start. Like, there was one that I had to deal with where it was like, I'm pretty sure this is a lot easier than I think it is, but it's like, you have a cylinder, you have a step, and this step has height h, and your cylinder has radius r. What is the minimum torque or minimum force that you need to make this cylinder go up this step? And like, you don't even know where to start. So one of the best parts is to break it down. What's the moment arm? What's the highest torque? It's always nice to just like break down a problem, right? That's all I'm trying to say. But moving on from there, no, that's what I want. So back to here. Second thing, solve for limiting cases. Now, what do I mean by that? when I say limiting cases, I mean like, oh no, I just revealed all my tabs. God damn it. Okay, so when I say solve for limiting cases, that's mostly gonna go for like just testing out everything. Just think like guess and check. That's what I'm saying. Guess and check. We're gonna do a guess and check problem, probably 2 of them, and something else that's really interesting is we can apply like solving for limiting cases for a lot of things regarding angles, right? So I think there was one, I don't remember the exact problem. I think it was like minimum force to like push a laptop over, right? I don't know if this was last year, maybe it was earlier. And we have this angle theta, and we're just gonna say like minimum force, right? And the equations were divided, the answer choices were divided into like some kind of equation, but every single one had either 1 minus cosine theta or 1 minus sine theta, right? And then some kind of like force here, right? Or like some kind of other thing here, like maybe like weight and the length or something like that, right? That's how torque works. But we had something like this, right, for each of the answer choices. And I can test for limiting cases for this, right? Let's say that our theta is equal to 0, right? That means that our laptop is like this, right? It is completely, this is 90 degrees, right? If I had cosine theta and theta equals to 0, right? That means that cosine theta is equal to 1, right? Cosine 0 is equal to 1. That's some unit circle stuff, right? So that means that the minimum force needed to push this laptop over is going to be 0. And that doesn't make sense, right? We're pushing on the laptop. What do you mean minimum force to tip this over is 0, right? So this is incorrect. Now, if we had 1 minus sine theta, right? If our theta is equal to 0, right? Sine of theta is also equal to 0, right? And we can even test this out the other way. What if our theta is equal to 90, right? That would mean that our laptop is completely flat. We need no force to tip this over. But this says that we need force to tip it over. So this is wrong. That's what I mean by limiting cases, right? So those are limiting cases. My throat hurts. I should have drank water. I'm revealing my tabs again. Stop joking with the camera. Okay, so final thing. Don't overcomplicate, but don't be tricked. What I'm trying to say is some problems are going to look easy, but be hard. Some problems are going to look hard, but be easy. Just like calm down, think every problem through. Break down a problem, solve for limiting cases. Those are going to be your big things, right? This applies to every test, but it's just nice to keep these in mind when you're doing FMA, right? Alright, so now that we're done with that, let's see if we can do some of the problems. Alright, so this is the worksheet that I handed out. I'm so sorry for giving you guys a worksheet. But let's start on this, right? A 470-gram lead ball is launched at a 60-degree angle above the horizontal. I can't see what's going on. With an initial speed of 100 meters per second directly towards a target on a vertical cliff that is 150 meters away, as shown in the figure, right? Or at least you can see the distance, right? So, ignoring air friction, by what distance does the lead ball, oh, that is the wrong key, does the lead ball miss the target when it hits the cliff wall, right? Okay, so I kind of set this up right now. So we have this cannon, right? This is at 60 degrees, right? We have a distance of 150 meters, right? We have a target here. We have an initial velocity, v0, of 100 meters per second, right? And we're trying to figure out how much does this drop? Because gravity exists, right? Gravity exists. And why did I do that so dramatically? Anyways, so gravity exists. I'm going to hide this for now. So that means we're trying to find this drop, right? So there's 2 ways of going about this. There's a smart way and the slightly dumber way. Let's first do the slightly dumber way, right? So we can tell that this is a 90-degree angle, right? So what we're getting here, remember how I said it's nice to know trigonometry? This is a 30, 60, 90 triangle, with this being 30 degrees, this being 60 degrees, and this being 90, right? And the sine length ratio for a 30, 60, 90 triangle is going to be 1 square root of 3, 2 in this order, right? We know this is not 150 degrees, this is 150 meters, right? So this side is 150 meters, so we know that this is 150 meters. That means that this side length is going to be 150 divided by 2, which is 75, and this is going to be 75 square roots of 3, right? That was so badly written. 75 square roots of 3, right? Okay, and these are all in meters. These are all in meters, right? Okay, so given that, remember our horizontal position is judged by x of t is equal to x naught. X naught plus v naught t sine theta, right? So, no. What am I doing? Cosine theta. I'm stupid. Okay, so let's start plotting this stuff out, right? At our final position, our xt is going to be 75 meters, right? So this is going to be 75 equals, we can say that this is our original position of 0, right? So we're going to say our original position is 0 plus v naught, which is going to be 100, times t times cosine of 60, right? Cosine of 60. Did I do this right? I did do this right. Okay, so cosine of 60. Remember our unit circle. This is going to be equal to 1 over 2, right? So that means we have 75 equals 50t. And that's also going to mean that our t is going to be equal to 1.5 seconds, right? All right, now that we have that settled, let's see if I remember how to do this. I haven't done this lesson in so long. Okay, so that's our first part, right? T equals 1.5 seconds. That's going to be important, right? Next, we're going to need to figure out how much this drops, right? What is the final height of this? And compare it with what it's originally supposed to be. So, we know that y of t is going to be equal to, again, y naught. We don't need that. Our starting point is 0. Equals v naught t sine theta, right? Minus 1 over 2 gt squared, right? Now, let's start writing this stuff out, right? Y of t, that's going to be our final. That's what we're trying to find. Y of t is equal to v naught 100 times 1.5 times sine 60 minus 1 over 2 gt squared, right? Let's keep it like this for now and look at something interesting. What is this equal to? This is going to be 150 sine 60 degrees. What's this? 150, the sine 60 is equal to the square root of 3 over 2. Oh, what a coinky dink. I wonder what that number gives us. Wow, what a coincidence. I wonder why. That's because our position, remember, the only part that's going to change from just going straight up, the only reason why we're going to drop is because of gravity, right? So that means that the amount of drop that we're going to have is going to come from here, right? So we just need to determine what negative 1 over 2 gt squared is. And that's going to be our drop, right? So remember, g is equal to 10, t is equal to 1.5. So this is going to be negative 5 times 1.5 squared, right? And this is going to be equal to 11.25 meters. And if we go back, where's OBS? If we go back to here, we can see that we have the answer choice of E, which is 11 meters. And that's going to be our answer, right? So that's the first way to do it. We can do the second way as well. So let's go back just a little bit, right? Let's go back to all the way here, right before we draw this triangle, right? And this is meters, right? Okay, so let's work from here again. Let's say we're just shooting this in a straight line, right? We know that our horizontal, we don't have any acceleration in the horizontal component. So when we determine the time that it's going to take, that time isn't going to be affected by the acceleration, right? So we can say we have a distance of 150 meters. We have it shooting out at 100 meters per second. Distance is equal to time divided by velocity. Or no, what am I saying? We know that speed is equal to distance over time, right? So time is going to be equal to distance over velocity, right? So our time is going to be equal to 150 divided by 100, which is equal to 1.5 seconds. Wow, that sounds really similar to one of the things that. Okay, I'm going to stop stalling. So 1.5 seconds, right? That's what we just got. we just plug it into the -1/2 gt squared thing again, and we get 11.25 meters again. That's the amount of drop. So much faster, so much quicker, but it's a little bit unconventional, but that's also going to be our answer, right? So no matter what, both ways, they both determine the answer that we're going to get E, right? Okay, so next, I can't erase this. Why can't I? Sorry. So next problem. I should scroll down a bit. So there's actually two parts to this problem. I'm pretty sure this is from an older test. I think like 2010, 2014. I don't remember. But let's go about this. So two cannons are arranged vertically, right? With the lower cannon pointing upward and the upper cannon pointing downward. Wonderful. 200 meters above the lower cannon. Simultaneously, they both fire. Muzzle velocity of the lower cannon is 25 meters per second. And muzzle velocity of the upper cannon is 55 meters per second. So I ask you, how long after the cannon's fired do the projectiles collide? All right. Let me adjust my brush size. There we go. Okay, so let's go back here. My camera's on again. I forgot that it was on. So we have two cannons, right? We have one on the up and one on the down. They're shooting at each other because that's how things are. This is 200 meters. We know that initial velocity for bottom is 25 meters per second, and top is going to be 55 meters per second, right? So let's think back to our equations, right? We can once again use those projectile motion equations, even though those aren't really conventional, but we can do, we know that there's not going to be a horizontal component. They're shooting directly upward and directly downward, right? So let's look at our yt, right? Yt is equal to y naught plus v naught t sine theta. We know that theta is 90, right? They're pointed directly at each other. So sine theta equals 1. We can just pretend it doesn't exist, right? -1/2 gt squared, right? Okay, this is also based on one of the kinematics equations that I talked about before. Oh, I need to hide my camera. All right. So we know that this is also really similar to one of the kinematics equations we talked about before, but this is what we're going to be going by, right? So let's plug some values in, right? So for 55 meters per second, right, pointing downwards, that means that our y of t for first cannon is going to be equal to, we have a height, we have an initial position of 200 meters relative to this lower cannon, right? Minus, remember we're pointing downward, right? 55t minus, we know 1/2 times 10 is 5, right? So 5t squared. That just simplifies things a little bit. For yt2, right, that's going to be for the second cannon. I can even color code this. I don't want to color code this. Is equal to 0, right? We're starting from our initial position, plus 25t minus 5t squared, right? So we're trying to determine the time that it takes for the projectiles to collide, right? So at the time that they collide, they're going to be at the same point, right? That's how collisions work. They're at the same point. So we're just gonna assume that like the projectiles are small enough for like contact to be like, I don't know. Anyways, so we know that means these positions have to be the same at the time of collision, right? So we can plug this in. So I'm gonna move this over. I cannot move this over. I'm sure all of you can hear my computer fan dying. But we can just say these two are equal to each other, right? So 200 minus 55t minus 5t is going to be equal to 25t minus 5t squared, right? I prepared so many colors and I'm not using any of them. So this is squared. So first thing, cross these off. Second thing, move this over. 200 equals 80t. T equals 200 divided by 80, which is 10 divided by 4, which is 2.5 seconds, right? So if we go back to our worksheet, that gives us B, 2.5 seconds. Wow, how long has this taken? This is already 34 minutes. Okay, we have B, 2.5 seconds, right? Next, how far beneath the top cannon do the projectiles collide? Now, this is not going to be hard. This is kind of tricky, though, because everyone gets messed up by the wording. It's stupid why everyone gets messed up, including me. So, 2.5 seconds, right? All right, we're trying to find the height below the top cannon. What is this height, not this height. So that's the part that messes up people, because it's below the top cannon, because you're going to think, oh, it's going to be this height. It's not that height. So t equals 2.5 seconds, right? Let's just plug it into one of these equations. Let's plug it into this equation. Why not? So 25t. 25 times 2.5 minus 5 times 2.5 squared, right? Let us plug that in. I'm pretty sure that's like 31 point something. Times 2.5 minus 5 times 2.5 squared is equal to 31.25. So this is equal to 31.25. Now that's our answer, right? No, that is not our answer, because our answer is determining what the height is below the top cannon. So we're going to actually have to do 200 minus 31.25. Now that's going to be like what, 168.75 meters. But if we look back at our answer sheet, I'm here now. Oh no, there's no 168.75. What's the closest one? It's 170 meters. That's our answer, E. So that's our answer, 170 meters. So remember to read the questions more clearly, right? All right, next, let's see if I can erase this first. So, a cannonball is launched with the initial velocity of magnitude v0 over a horizontal surface. At what minimum angle, theta minimum, above the horizontal should the cannonball be launched so it rises to a height h, which is larger than the horizontal distance r that it will travel when it returns to the ground? And we have a few answer choices, right? So, let's think about this, right? I'm going to keep my camera on for a little bit. We're trying to find our height and our range and find a comparison. Where can we do that? Oh, hey, look! I'm going to use purple because that's what I wanted to do fundamental concepts with. Oh, look! H is equal to v0 squared sine squared theta over 2g. That might be useful. R is equal to v0 squared sine 2 theta over g. That might also be very, very important here. So, we know that our minimum angle is going to be where these two are the same. Of course, if we're going to increase our angle, we're increasing our height and decreasing our range. But that doesn't matter. We're just trying to find the minimum, which is where these two are equivalent to each other, right? Okay, so that means let's set these equivalent to each other. Let's do black. v0 squared sine squared theta over 2g is equal to v0 squared sine 2 theta over g, right? Now let's do some canceling, shall we? Cancel this, cancel this, cancel this, cancel this. We have sine squared theta over 2g is equal to sine 2 theta. What am I doing? Sine squared theta over 2 is equal to sine 2 theta. Now, there's two ways of going about this, right? First way is being smart, right? I don't like doing that. But the way to being smart is, trigonometric formulas. Okay, so the first way is, sine squared theta over 2 is equal to, we know that sine, I need to move this. I don't need to move that, actually. I regret that decision. There we go. My voice hurts. Sine 2. We know that the sine fundamental concept. We know in trigonometric dual identities that sine 2 theta is equal to 2 sine theta cosine theta. My writing is bad on purpose. We know that, so we can just plug that. We can just plug that in here. So this is 2 sine theta cosine theta. Let's cancel this and move this over to make this force of sine theta equals 4 cosine theta. Move the cosine over, and then that becomes tangent theta equals 4. Plug that in with the inverse. Theta equals inverse tangent 4, right? You can plug this in. This is the same answer as what I'm going to do next. You know what you can also do next? Remember how I said guess and check? Guess and check. Just plug it in. I'm just going to tell you this is equal to 76 degrees, right? Theta is equal to 76 degrees. Just plug it in here. Just say like sine squared 76 divided by 2 is, and then plug in, you know how to plug in stuff. So You can guess and check for this. You can do the complicated way over here. That's the answer. This is the answer. It's 76. We can even go back to the worksheet. It's 76. It's A. 76. Okay. Yeah. Anyways. So there's that. I'm gonna start erasing this and then move on to the next problem. That is not the next problem. Oh my god, I forgot how much more I had left. So you're given a standard kilogram mass and a tuning fork that is calibrated in hertz. You're also provided with a complete collection of laboratory equipment, but none of it is calibrated in SI units because you're in America. Everything sucks. I'm kidding. You do not know the values of any fundamental constants. Which of the following quantities could you measure in SI units? First is an acceleration due to gravity. Second, speed of light. Okay. We know how this works, right? I remember I had this. Does that work? That works! I'm not smart. You are gonna go here. Actually, no, you're just gonna be gone. So let's go by this. This is not perfectly framed, but we can start listing this out, right? First, why am I using blue now? First, we have an acceleration, right? An acceleration. Second, we have speed, right? What's the third? Third is density, right? Density. Fourth is the spring constant. Now, okay, this might be a little bit early to talk about this. And 5 is air pressure, right? Alright, so we can do this the smart way and pretend we memorized all this, or we can do this the dumb way because we didn't memorize this. So let's go back here. Let's go back here. Let's go back here, and let's go all the way back here, right? So first thing, we have acceleration. This is LT negative 2, right? So that's our first thing. LT. I'm gonna do crita. This is equal to LT negative 2, right? All right. Next, speed. This is velocity. LT negative 1. We already talked about that. Density. That's mass divided by volume. I'm gonna assume that it's gonna be mass divided by volume, right? And if we check back here, density, right? Yeah, okay, mass divided by volume, right? Pressure, that's force over area, right? Pressure, that's force over area. So, force, you can just think force is equal to, think about the equation that we're given. Force equals mass times acceleration. So that's m times L over, am I doing this right? Yes, T negative 2, and then times area, divided by area, so times L negative 2, right? So that means that we have pressure is equal to force divided by area, right? So that means that we're going to have, I'm assuming ML negative 1, T negative 2. Am I right? I am right. Okay, so that's one thing. And finally, we have our spring constant. Now, I don't think our spring constant is actually listed anywhere here. But, okay, I guess we're going early a little bit. We have F equals MA, right? For spring constant, F equals KX, right? Okay, let's remove this stuff first. So, this is going to be, what? ML negative 1, T negative 2. Okay, so for spring constant force, we know that that's going to be equal to ML T negative T squared, right? That's how this works. This is force. We know that for springs, F equals Kx, where X is going to be our position, and K is going to be our spring constant, right? So X is going to be denoted as L. So all we have to do to find our spring constant is going to be equal to F over X, which is going to be ML divided by T squared times 1 over L, right? That cancels off the length. So that means our spring constant is going to be MT negative 2. Now let's revisit what we have, right? We have a kilogram mass. That is a mass. We have a tuning fork calibrated in hertz. Hertz is denoted by 1 over seconds, right? So that means we have a mass. We have a time, right? These are the measurements we have. Let's go by these one by one. This has length. We can't do this one. This has length. We can't go by this one. This has length. We can't go by this one. This has mass. This has time. This one works. This has length. This does not work. Our answer is D. I went by that fast. You can slow it down, but hopefully that makes sense. This is what I'm talking about when I talk about dimensional analysis. We have units. We're given units. We try and determine which one's matched. If you do it more often, it's not as hard as it seems. But that's what this is. Let's move on to the next problem, shall we? So, next problem. Next problem. How does the speed of waves on a string depend on the mass m, length L, and tension force T? Alright, so let's go back. Let's go back here. We have, we're trying to determine our speed, right? Trying to determine our speed. We have our mass, we have our length, and we have a tension, which is actually our force. We're going to denote this as F for now because I'm too lazy to confuse myself, right? So, remember what we said. Force is going to be equal to, what am I doing? Is equal to m times L divided by t squared, right? We know that our speed is going to be equal to L divided by t, right? Meters per second, right? This is newtons, right? Newtons are kilogram meters per second squared. And again, F equals ma. Kilogram meters per second squared, right? Okay, so we have our force. We have a mass. We have length, right? Let's start determining this. First, we have this t squared on the bottom, right? So that means we're going to have f, the square root of f, right? So that means that that's our starting point, right? We have f, which is going to be equal to square root of ml over t squared. That's going to give us square root of ml over t, right? We have this t done, right? This is done. Now we just need to sort out this top part in order to make this L, right? First thing we can do, we have no m in here. So let's take out that m by putting it on the bottom, canceling this out, right? Next, we have this L, but currently we have a square root of L on top over t. Let's get rid of that square root by multiplying once more by L. This is now equal to L squared divided by t squared. Square root of this is going to be equal to L over t. Our answer for how the waves, the speed of waves on a string, depending on mass, length, and force, or tension force, is going to be denoted by T, or let's just say F. F L divided by T, right? And we can even double check this. This is going to be equal to ML over T squared times 1 over, why is there T there? M. Times 1 over m times L over 1. These cross out. This is squared. This is equal to L over t. That is our speed. That's how this works. This is how dimensional analysis is gonna work. I'm going really fast right now, but you can just let me know. Just let me know. I'll slow it down. I'll explain it more. But that's how this works, right? So that's how the speed of waves on a string depends on mass m, length L, and tension force t. There's probably like one problem. This is sort of rare to see on the test. So, part 3, error propagation. I'm running out of time. Shoot. Alright. I think I'm only going to be able to go through this first one. So, in an experiment to determine the speed of sound, a student measured the distance that a sound wave traveled to be 75 plus or minus 2 centimeters, and found that the time it took for the sound wave to travel this distance to be 2.15 plus or minus 0.1 milliseconds. Assume the certainties are Gaussian, the computed speed of sound should be recorded as this. So, let's go back here. And let's do this as fast as possible, right? So, we have 75 centimeters, plus or minus 2 centimeters as our distance, right? And we have our time as 2.15 milliseconds, plus or minus 0.1 milliseconds, right? So speed is equal to distance over time, right? We know that. So how are we going to do error propagation? Now, if we look back at our little error propagation thing, first of all, this delta, this is our uncertainty. Just how our big delta, this delta, is equal to a change in something, this small delta is also equal to a change in something. So I believe it was like this. Delta A divided by B is going to be equal to A divided by B times the square root of delta A divided by A squared plus delta B over B squared. This is going to be our percent error, right? So this is going to be like 0.1 divided by 2.15. So let's just directly plug in from here, right? So we have 2 divided by 75. 2 divided by 75 squared plus this what am I doing? Okay, so 2 divided by 75 squared plus 0.1 divided by 2.15 squared, right? And then the square root of that, right? So let's do that right now. Here, 2 divided by 75 squared plus 0.1 divided by 2.15 squared. That's going to give us like a square root. This is going to be around 0.05 or around 5%, right? Now let's do A divided by B. The problem is this is in centimeters, this is in milliseconds, right? We're trying to find the meters per second, right? So that means that we're going to have 0.75, right? Divided by 0.00215. Let's see. Times 0.75 divided by 0.00215. That looks about right. Let me see if I did this correctly. I plugged it in wrong, but yeah, so this is what we're going to be getting, right? 75 centimeters divided by 2.15 milliseconds. Convert that to meters per second, and that's going to give us around, as it states here, I think 349. And plus or minus, we're going to do 349 times around like that 0.05, right? And that's going to give us, so 0.05 times 349. That's going to give us around 19, right? And I didn't get the exact calculation, but this is going to be around 19 meters per second of uncertainty, right? So if we look back at our answer, that's going to give us answer choice C. For this last one, the big thing to know, this is another multiplication one. When we do average, the average is going to be like the standard deviation, right? So I'm going to clear this really quickly and see if I can get this before it's 145. So when I'm saying average of some results, I'm doing the standard deviation. Because if we think about this, let's do standard deviation of the population, right? Standard deviation of the population is going to be equal to this sigma x mean minus x of our value, right? Squared divided by n, right? This is uncertainty, right? This is how much the data varies from the mean, right? So if I take every possible combination of like variance, right? This is going to be the variation from the mean, right? So since this is just our this is our uncertainty, right? So this is going to be equal to our delta of x squared divided by n, right? And x, this is going to be sum of all averages. So how should I put this? This is going to be the average, right? Squared divided by n, right? So that means if we were to do a test 10 times, that means that it would be our uncertainty times the square root of 1 over n. So if we do 10 trials, then our uncertainty is multiplied. Let's say our uncertainty is like 0.1. If we do our test 10 times, that means we're multiplying by 1 over the square root of 10, right? this is our new uncertainty if we do our test 10 times. If I do the test 100 times, this is our new uncertainty. 1,000 times, this is our new uncertainty. That's how averages are going to work. But that's going to be all I'm going to cover this video. If you really want the answer choice, I'll say it. But for now, that's all I have the time for. If you want me to do this, I'll go do it. But thank you so much for listening into the first day of the FMA Club. We're going to be having our next one, I think this Wednesday as well, on dynamics and kinematics. I think kinematics, it's going to be that position, velocity, acceleration stuff, maybe even a little bit of dynamics, maybe a lot of some other stuff that I didn't cover. But that's it. That's all we're going to be doing this week. And thank you so much for coming, and I hope you have a great rest of your day. See ya. Bye.